All right, guys. So let's start for today. Um, I think you guys must have gone through all the lecture materials. So if you look at the major chunk of this week, it's basically uh, dealing with uh, stability of discretization schemes. Of course, we have consistency, convergence, and stability. So basically, stability is most more important aspect in this uh, while choosing a discretization scheme. So let's get started for today. Today, what we are going to do is we have this equation. It's called convection diffusion equation. Actually, this is a pretty much the same uh, like a general form of equation for any governing equations. If we look at it, this phi can be any quantity. It can be mass, momentum, or energy. So if there is a mass, this diffusion term won't be there. It will become a continuity equation. And if there is a momentum, let's say rho u, this would be a momentum equation. Similarly, if it is a rho e, let's say, it would be a energy equation, basically. So we what we will try to do today is we will try to analyze the stability when you model this convection part of this equation, not the whole diffusion equation, also just convection part, because the time derivative and diffusion equation would be pretty much covered in the lectures, right? So we will just understand how to do stability analysis for the convection part of the equation, and we will also try to come up with a very good, a very important condition for stability uh, by doing this. So before getting into the concepts, do you have any doubt from the previous lectures or sessions? If you have any doubts, you can ask me now. Divagar, Uzair, anyone? Siddharth, Benison. So today we have very less
No,
number. Uh,
no.
so I might keep on calling your names.
From my side, no doubt, sir. I
I
just
think
want to let you
uh,
know.
I think
Yeah.
Uzair had some doubt in last lecture. I thought of clarifying him in the last class, um, but he was not available. Um, can you come? Can you come again? What was your doubt? You asked something about higher order schemes, if I remember right.
Yes, sir.
Uh,
Yes, sir. So actually, I had doubt in that part only. It's like how it's like about center differencing, forward differencing, and backward differencing in that part. It's of how higher order scheme. I didn't understood that part.
you understood what is central, backward, and forward differencing, right?
Yes, sir.
So, but you couldn't understand the higher order discretization schemes, right?
Yes, sir. Yes, yes.
So, it's actually the way if you look at the truncation term, um, if it is more than second order, we usually call it as higher order. So, it is actually um, like you will come up with a scheme such that the leading term or the truncation term becomes high, so that your what do I say, the solution is captured more accurately. That's the main purpose of going to higher order scheme. The derivation purpose, if you want to know how it is derived, you should go back and check any one of the CFD books, or go back to the lectures. It's actually simple. You can derive it by yourself. There is something called polynomial fitting method. You can use it to derive it for higher order derivatives also. So here we solve only for this first order derivative, right? First order derivative, and we'll also go for second order derivative. So if you go to um, let's say like vorticity stream function equation, there is a fourth order derivative. So for that, you still don't know how to solve it analytically, so you will discretize it. For that, you use polynomial fitting method. Those are a little bit advanced method. It's not like it is one step higher than this how you derive, but it is simple. Actually, you can go through books like Freysiger and Perick, Computational Fluid Dynamics. You can go through those books. If not, you let me know in coming lectures. I might able to provide you some materials. Okay. But for beginner level CFD,
Okay, sir.
you can go ahead with central and upwind differencing. If you are comfortable with these two schemes, you will automatically understand other schemes also. Like you go through once and you let me know. If you still face any difficulties, I will help you. Not a problem. Okay.
Okay, sir.
All right. So if you guys don't have any doubts, I will. Yeah, Divagar, do you have any doubts?
Sir, yes, sir. Commercially, are we using this polynomial method in the market?
So
In either in commercial tools or
right. So actually,
Yes,
this
sir.
polynomial method, all these things are for deriving the discretization schemes. So in commercial CFD softwares, our codes, what they do is the discretization scheme is already developed. You no need to develop that scheme again and again. Okay. So this central differencing is already developed. You are just going to use it. Similarly, there are few schemes like quick schemes, compact schemes. So those things are already developed. They just implement it in the software. Um, Basically, if you are doing pure CFD research and if you have a problem, if you have stability issues with higher order schemes, like if you want to come up with a new scheme which is more effective than the uh, present available scheme, you would take a different approach. It won't be even polynomial. It would be a little bit advanced approach. It comes in pure CFD research. Basically, what you will do is you won't derive the discretization scheme. The schemes are already available. You will just implement it and get the results. Basically, that's what all the CFD software, like all the CFD practitioners will do. um, we won't derive any schemes. So here why we are showing is you need to understand the basic concept like central and upwind, how it affects the solution, what is the characteristics of these schemes, where when to use what. So these things and all these things you will understand by knowing the basics like central and upwind schemes. That's why we derive it and we show you. Uh, but basically in commercial softwares, we don't use anything like that. Is that clear? So schemes are
Yes,
already
sir.
available. We no need to derive it. That's what I'm telling. So the schemes can be derived in any ways. Like from Taylor series, you can derive it. From polynomial fitting method, you can derive it. There are few more methods also, research-based methods. You can derive it from there also. But we no need to derive every time when we run a simulation. Right? We'll just use those schemes. Right? Okay, so what we will do is, if you have gone through your assignments, this week three's assignment, you would probably see that like all the questions are straightforward. I no need to, solve it. Like there is no solving kind of question. One question I've gone through is stability question. That's why I thought maybe I will show you how stability works so that it will be helpful for you to solve that equation. So we won't uh, solve the assignment problem here, but I will show you that how to do that stability analysis so that you can solve that assignment problem. So that's the agenda for today. Um, let me go ahead. So here we have the equation, general governing equation we have. So what we are doing is, first we will ignore this diffusion term. So because the diffusion terms are already dealt in the lectures, you can go back and revise it. So we will, you know, we will ignore it or we will neglect it. It's better not to put zero, but we will just neglect it. So the remaining equation becomes like this, the A equation. So it's just dou phi by dou t equal to minus u dou phi by dou x. So now you guys are expert in approximating these derivatives, right? So what is this? What is this scheme? You guys guess the time derivative.
Forward, sir.
Yeah. So it's a,
Forward.
yeah, it's a uh, forward time scheme. We usually call it as Euler's scheme, Euler's forward time scheme. So if we let me write it down. This is actually forward time. So why we say forward time is, so we are marching in time. So from initial condition, we will go to next time step. So it is a forward in time. It's like forward in space. Like we have forward scheme, right? Central, backward, forward. Similarly, in time, it is forward in time. And similarly, we will take a first order scheme for space. This we all know that it's a central differencing scheme. Similarly, we have a upwind scheme or backward scheme. So these terms are interchangeable. So you may notice that I'm using approximate sign because it's an approximation. And so this is, if this is the equation we have, what we will do is, for every term, for every derivative term, we will try to approximate like this using the discretization scheme. That's the whole point we did. That's the whole point of discretization, which we did for last week. So what we do is, we will discretize this for each and every term and we will substitute in the equation. So after we substitute in the equation, let's say we are substituting the central in space and forward in time into the equation A. Uh, Divaga, you have some doubts?
Sorry to interrupt you, sir.
Yeah, no problem. Yeah.
So actually, uh, sir, with respect to space, that means dou pi by dou x, we can use either central or backward or forward. But for the
Right.
time, actually, dou pi by dou t, it must be the forward time only, na, sir? Other two things actually may not applicable. Am I right, sir?
Right. So, yeah, in forward time, you may central and backward may not be applicable. True, but it's not. You can still implement central in time also. The only thing is, it has a starting problem, because at time t equal to 0, we don't know the value at time t equal to minus 0.1, right? So at the first time step, you
Yes.
use forward time, and from the second time step, we know the first time step values, and we are going to predict the third time step value. So we can
Yes,
use,
yes, it's kind of mixed one.
so we can, at that time we can use central, we can use backward also similarly. So those are like, those you can try, but it has a starting problem. At first we can't, at first time step we don't know the value at t 0 minus. So that's why people always use forward time. You can We can also try central in time also, second order time. That is also possible. It Everything is possible. You can do either way. Only thing is, your solution should be more physical, and it should the solution should have the physical meaning. It shouldn't be non-physical, solution. So until unless everything is fine. So that's why we come up with a very sophisticated scheme, such that it will produce us more physical solutions. Is that clear, Divakar?
Yes, sir.
Okay. So let's take these two, forward time and central in space. If we assemble it into a equation, this is how the equation looks. And so actually, um, you can either, this would be j at j node. So you can either write these things at nth time step. N is actually previous time step, n plus 1 is present time step. Let me write it down here. Time plus 1 is present time. Okay, so you can either put n. If you put n, what happens? This become an explicit scheme. So what do I mean by explicit scheme is, if you are integrating with respect to time, or so actually this is basically kind of integration with respect to time. And if the function here is evaluated from the previous time step by no, evaluated by like in previous time step we already know the values, right? By knowing, if you evaluate by the known values, then you will call it explicit scheme. Like if we don't know the value, like if you evaluate at n plus 1, n plus 1 we don't know, present time step we don't know, but previous time step values we know. So if you evaluate this at n plus 1 time step, then it would become an implicit scheme. So what we will do here is, we will choose an explicit scheme. We will try to do an explicit scheme. We will evaluate this function at nth time step. Okay. um, and then we will try to understand the stability of this scheme. So first we have FTCS scheme, forward time and central in space. You can see here j plus 1 and j minus 1. Similarly we have backward space, j and j minus 1. So we won't be doing both the stability analysis for both. This would be left for homework. You can do it by your own, but we will do a stability analysis for forward time, backward space. Okay. So why we are doing this is, we will understand there is an important parameter we will come up with while doing this. If we rearrange this equation, we will get this star equation. So I'm just what I did is, I multiplied delta t here and I took phi j at n this side. So we will get this star equation. So this is the equation we will implement in any software, or this is the equation actually we need to solve to get the solution. So how will you solve it? Do you guys have any doubts till now?
No, sir.
So actually, what you will have is, you will have something called mesh. Okay, mesh or grid, and let's consider a 1D situation here. This would be j. This would be j plus 1. This would be j minus 1. This would be j minus 2. This would be j plus 2. Like dot dot dot. Similarly, so now what we will do is, the let's say this is the domain, the whole domain. Let's say j is from uh, 0 to m, let's say, because n we are already using for time step. We will take m. Okay. This is the whole domain we have, and for the whole domain we need to solve this equation. We need to solve this equation. So what we are trying to do is, we are trying to divide it into a small domains, and we are going to solve the star equation for each and every node. So now if we have m nodes, we are going to have m this star equations, and since here everything is known, because everything is in n time step, so let's make it explicit. Everything is in n time step. So at time t equal to 0, we know the initial condition. Based on initial condition, we can find what is the phi's at n plus 1. And after finding all the phi's at n plus 1, we will find the phi's at n plus 2 by by using the values at phi n plus 1. So if we go, this is what we call as explicit scheme, and what we actually did here is this is an algebraic equations. If you look at these are algebraic equations, and what we basically did is we converted this partial differential equation, one equation, partial differential equation for the whole domain, into a system of algebraic equation, because algebraic equations are basically easy to solve. It actually comes up with ax equal to b format. Of course, in this explicit formulation, we no need to solve anything, because right hand side everything is known, only left hand side is unknown. So you don't need to solve, you just need to substitute the values once you find those values. But if you make it n plus 1, let's say, if you make it n plus 1, then we have 1, 2 and 3. So we have 3 unknowns, and we have like m equations, right? So three unknowns, but we have m unknowns. If you so, because each and every node we don't know, and we have m equations and m unknowns, so we will be able to solve that equation, because it's a system of algebraic equation, that too linear algebraic equation. So that is how we usually solve in any softwares. Also they solve like this only. That's why we discretize it also. We just try, we couldn't solve PDE, so we discretize it, we convert into a bunch of algebraic equation, and we are solving that algebraic equation. So now let's come back to that discussion. So this is the equation we need to find. This is the equation that we got by using the discretization schemes like forward time, backward in space. Now we need to know whether the scheme is stable or not. When I say stable, what do I mean is, so these are all approximations. By doing this approximation, we have an error, and if I if I march in time, will this error increase, or will this error decrease, or it the error doesn't change. So as you march in time, at first time step you will have some error, at the second time step in addition to that error you will have some more error, because all of these are approximation. So if this error continues to increase, then your scheme is going to become unstable. So that's why this stability analysis is very important to understand whether the scheme would be unstable or stable. So we will start with this statement. So we have, let's say, phi j bar is the exact solution which satisfies the star equation. So this exact solution will always satisfies the star equation, but now we are computing a numerical solution. This numerical solution should satisfy star equation as delta t tends to 0 and delta x tends to 0. Okay, so there is always a error associated with this numerical solution. So let's write that error as this. So epsilon j is actually equal to phi j minus phi j bar. So a numerical solution minus the exact solution will be the error. Okay, so if you write it for the nth time step, basically phi j at n minus phi j bar at n. Similarly, if you write it for n plus 1 time step, this is just an error. Error I am representing as epsilon j. Let me write that also. Error phi j at n plus 1 minus phi j at n plus 1. So what we are going to do is, we need to understand how the error progresses. So what we will do is, we will substitute this phi j. So what we can write this as phi j is equal to epsilon j minus plus phi j bar at n plus 1, right? So what we will do is, we will substitute this term, in our star equation. Okay. So when you substitute this in star equation, what happens? Epsilon j at n plus 1 plus phi bar j at n plus 1 is equal to epsilon j at n plus phi j at n. Yes, Divagar?
Yes, sir. Sir, actually, sir, first of all, I'm not interrupting, like it's
No,
not
no, no, no,
disturbance,
no problem. So
right?
actually,
Like I
the
can ask
whole,
you the,
yeah, yeah,
yes, sir. Thank you,
yeah, yeah.
sir. Thank you, sir. Thanks for that freedom. Sir, actually, you have mentioned is there actually, like from the bottom third line, where you actually marked in the square rectangular dots, pi j equal to epsilon j, which is error plus pi j bar n plus 1.
Right.
So n plus 1 is the current thing.
Yeah, n plus 1 is present time step. So,
So
yeah, any,
present time step.
yeah,
So when you
mhm. Yeah, go ahead.
So when you are mentioning n plus one, which is the present time step, yeah, pi, when you are mentioning n plus one, which is present time step, then the left pi is the which time step, sir? Whether the present one or obviously it's supposed to be present one, no, sir?
So both should be at the same time step. Okay. So phi should be at the same time step. Phi
Exactly.
bar
Thank
j
you,
is
sir.
also at the same time step. So if it is at n, this will also
Exactly.
be at
Yes, sir.
n.
Yes,
If
sir.
it is at n plus 1, this will also be at n plus 1.
Yes. Yes, sir. Yes, sir. I understood. Thank you, sir.
Okay. So so what we will do is this error needs to be always numerical minus exact, or it can be vice versa. Anyway, it's fine. So it's just an error term, right? So this minus that minus this, it will be positive or negative, but the the magnitude is going to be same.
Sir, I got one other doubt. Can I ask?
Mm-hmm, sure, sure.
Sir, actually, when we are computing the error epsilon j is equal to pi j, which is nothing but the numerical one minus pi j bar, which is nothing but the analytical one.
Right. Exact solution.
So this error, yes, sir, exactly, sir. So actually, this error for each iteration, it will calculate, sir.
Yeah, so actually we are not going to calculate, we are just representing and we will understand whether this
Ah,
error increases or decreases. We won't calculate it while doing a CFD
ah,
thing. But the thing is here is we won't be able to because we don't know analytical solution now for a lot of the
exactly, sir.
problem.
Yes, sir. Yes, sir.
So
Understood.
yeah,
Thank you,
we
sir.
don't have exact solution. So what we will do is we are just
Thank you, sir.
representing it like this, and we will understand how error behaves for this discretization scheme. So if the error reduces, it would be it has nothing to do with analytical solution. So because you are approximating derivative for a numerical scheme, right? So it has nothing to do with analytical simulation, analytical solution. It's just how close your solution with the analytical. It's just a error term is not dependent on the solution. Only thing is it depends on the scheme, and whether it increases or decreases is what we are going to find.
Really understand, sir. Thank you.
Okay. So uh, so what we will do is, yeah, we will go ahead and substitute. So this is going to be epsilon j at n plus 5j at n, actually 5 bar, and minus 5j minus 1 at n. So this would be epsilon j minus 1 at n plus 5 bar j minus 1 at n. So now we know that uh, the exact solution is going to satisfy the equation. So we can strike it out the exact solution term, right? So actually we can separately write these things. So resulting equation would be epsilon j at n minus u delta t by delta x times epsilon j at n minus epsilon j minus 1 at n. Right, this is the error equation we have. uh, Basically this exact solution is going to satisfy the star equation, so that's why we cancelled out the term, right? So now we have this error equation. um, Now we need to understand whether the error grows or not. So usually if you look at the error term, so when I say error, again we'll mark a stencil here. So this is the grid, and the exact solution will be there, and the numerical solution will be there. So the difference between these two, if I mark here, so it will be like this, oscillating here, like it will, because solution, numerical solution and exact solution will have a few differences, and it may not also be equal. Like yeah, Uzair, you have some doubts?
Sir, sorry to interrupt.
Yeah, no problem.
Sir, actually, means like when we do conversions, means like when we do iterations in that CFD, so when we solve CFD problem, so in that we put iterations, and then the solution automatically stops if we use the commercial software. Okay. So sir, how we can means is the error reduces, or means like error might increase in some iterations also.
Uh, so there is a possibility that error increases or decreases. Only thing is it tries to find a best approximation based on like the scheme, and the solver tries to find out the solution. At that time it can overshoot or undershoot. So error can increase or decrease. But eventually as time increases, error should decrease. That's how you will know that it has converged. So convergence means error should decrease, and there shouldn't be any big variation in the solution. Right? That is how you will know the convergence.
Okay, sir. Thank you.
So yes, Nidara.
Hello?
Yes.
Sir, could you please explain that how you cancel the 5J terms, sir? 5.
Yeah, sure. So yeah. So this can be written as, let's take this equation. So so if you see, this can be written as plus phi j bar n minus u delta t by delta x times phi j bar n minus phi j minus 1 bar n. This side it will be phi j bar n plus 1, right?
Yes, sir, right.
Right. So what you do, you take this to the other side, okay? So if I do that, what happens?
Minus 5J
Minus phi j bar n
n plus
plus
1.
1. Now you go back to this statement, you see this equation. This phi j bar satisfies the stars equation, right? So if you take this phi j to the other side, it will be minus phi j bar j, it will be minus phi j n plus 1, right? This side would be 0.
Right, sir, right.
So I'm just, so this whole term is actually equal to 0.
Oh, okay. Fine, sir, fine. Thank you, sir.
Whole term is equal to 0 because of
Okay.
star equation.
Okay, sir, okay. Thank you very much, sir.
So that's how we got this equation.
Yeah.
Okay. So
Yeah,
now,
thank you.
yeah. So now we know that error will vary randomly within the nodes, and we won't be able to understand how the error increases or decreases. That's why we have a wonderful tool called Fourier analysis. Okay, so this we will represent it as using a Fourier series. So if you don't know what is Fourier series, it's just if you have a random signal, if you want to represent that signal, what you will do is you will consider sine and cos terms with proper weightage, and you will add lot of sine and cos terms, and add a proper weightage to it to represent the some random signal. That's the very poor way to put it, the Fourier series, but you can go back and look at what is Fourier series and how it is useful. So what we are going to do here is, we are not going into the details of Fourier series, but what we will do is we will represent this error as a Fourier series. So how we will represent the error is m to n m a summation of m equal to 1 to m. It is up to it's our wish to take whatever m we want. This m is not equal to number of nodes. Okay, so let me be clear there, and this we can write it as power I kmx. So this e power I kmx, we know that it's nothing but cos kmx plus I sin kmx. Okay, so so with cos and sine terms, and with imaginary and number of terms like that, you can represent any signal, like a square wave, any signal in terms of Fourier series. So this would be helpful in analyzing the behavior of the stability of our scheme. So what we will do, we will quickly write it down. So for epsilon j as a function of x, we can write it like this. Similarly, if it also a function of time, what we will do is we will add another e power at term. Okay, so am e power at e power I kmx. So this is the error term, the whole this error we have here, this error non-linear like oscillatory error we have, this we are going to represent it as um, this one, as a Fourier series. So now now we have in our error equation, this is called error equation. Now we will substitute this Fourier series for each and every term. So how would we write the Fourier series term is epsilon j at n. What you will do is you will it would be same, like am e power at e power I km x. Now epsilon j minus 1 at n would be summation of m equal to 1 to m am e power at, because everything is at time step, at n time step, that is previous time step. So we will have km, but here it is x plus delta x, actually x minus delta x, because we have j minus 1 here. So let me quickly correct it. It will be x minus delta x. Similarly, we have one more term called n plus 1. So for this, can you guys guess what would change in that error term?
It will be same, only x plus del x will be there, sir.
So this is at it is at j only. Okay, so for j we no need to change the x term, it would be still x, but it is at time n plus 1, so there is one time step is there. So what we will do, t plus delta t will put. Okay, so this is how you will
Okay.
represent for each and every node, for each and every time step. So this we can rewrite is as summation m is equal to 1 to m am e power at e power I km x and then e power I km delta x. This we can rewrite it. Uh, Similarly, if we rewrite for the other one, e power at e power I km e power a delta t. Okay, so now let's
That is
substitute this.
the second equation in the second equation e power minus I km del x, no sir? E
Right,
j
right,
minus
right,
1
right, right,
in the time step of time.
right. Fine. All right. So let's substitute in the error equation. Substitute in the error equation. Um, what would happen is this would be at n plus 1. So it has lot of common terms. We can neglect it and I can simply write it as e power a delta t is equal to e power, this is at j 1, 1 now. So this won't have this, 1 minus u delta t by delta x times epsilon j at n 1 minus, so I'm just cancelling all the uh, you know the common terms, and then I'm writing a final equation like this. So if you substitute epsilon j n plus 1, you are going to have this big term and e power a delta t will be there. Similarly, at epsilon j you will have this term. So actually I am cancelling all those terms, all the e power at, e power I km x in each and every term, so that I will end up with only this equation, right? There is still summation of m equal to 1 to am is there, but let's not worry about it. Uh, our aim is to find this thing. Okay, is that clear, everyone? In the interest of time, I'm just skipping little bit steps. Um, you can derive it also, no problem. So now, after getting this, what we will do is we will let's simplify this. We will write this as c, okay, some constant u delta t by delta x. Okay, this is c. Let's write it like this. And now we will also so if we substitute that and if we write it, it will become e power a delta t is equal to 1 minus c times 1 minus e power minus I km delta x. Okay, the equation we have. Now um, um, if our aim is to understand whether it is stable or not, so what would be the condition which says the scheme is stable? Only thing we know is the error shouldn't rise from one time step to next time step. So how we can put that is, it is called as amplification factor. You guys must have already known. It's g, it's nothing but epsilon j at n plus 1 divided by epsilon j at n. Error at n time step and error at n plus 1 time step. So if it want to be stable, how should g be? Can you guys guess? So error at n plus 1 time step should be more than error at nth time step, or it should be less?
Must be less than or equal to 0, sir.
Right, it should be
Uh,
less than or equal to 1 actually. So you no need to be 0. If it's a, if it has to be 0, what happens? Error at n plus 1 would be 0. So that is not possible, right? But only
you are
thing,
right, sir.
yeah,
Actually,
only thing
zero
is,
zero cannot be. Yeah.
yeah,
Sorry.
only thing is it should be this condition should be satisfied. This condition can be satisfied if the epsilon j comes here, you will get 1. So this is the amplification factor g, which is error at n plus 1 divided by error at n. If we let's see, if we substitute that error representation here, a Fourier series representation here, it would be summation m is equal to 1 to m am power a t e power I km x and e power a delta t, because it's at n plus 1 divided by summation m is equal to 1 to m am e power a t e power I km x. Like if you see, these are common terms. If we remove it, it is equal to e power a delta t, and this term is still there. Okay, but we are just for simplicity of writing, we are just removing it, we are just ignoring it, but it is still there. And if we look at this g, okay, this g and this equation are same, right? So we can write g as, we can write g to be 1 minus c times 1 minus e power minus I km delta x. Okay, so this is g, and for any k is nothing but the coefficient in comes from Fourier series. For any k, we want this uh, for any km and x delta x, we want g to be less than or equal to 1. So one way to make sure is, one way to come up with a condition, so because it depends on delta x and it also depends on delta t, because c is nothing but u delta t by delta x, so it depends on c. So one way to make sure is, so modulus of g square should be less than or equal to 1. This is this uh, condition and this condition both are same. G is less than or equal to 1 and this g square is less than or equal to 1, both are same, because if it is negative also, it's going to be less than or equal, less than 1. Is that clear till now?
Sir, the last 2 points you have written, sir, for km and del x g less than or equal to 1, and the next step also. Can you explain once again, sir, those two
So
lines?
right.
Thank
So
you.
if you look at this, for stability condition, for stability, we are interested in stability. For that we need g should be less than or equal to 1, right? And now for this scheme, the g is governed by this part of the equation, 1 minus c into 1 minus e power I km delta x. Now for any km comes with the Fourier series. So for any km, for all km, whatever km would just a constant, it would be a constant. For all km, whatever km be, you want this g to be less than or equal to 1. Okay, this can also be written as modulus of g square less than or equal to 1. Okay, so if it is modulus g less than or equal to 1 and modulus of g less than or equal to 1, both are same. Okay, and I'm just squaring it so that it would be easy for us to analyze this uh, equation. Okay, this part is
Yes,
clear.
sir, clear. Clear point.
Okay,
Yes,
so
sir,
yeah.
clear.
Okay. So now, if you want to find modulus of g square, so it's you can, let's write it separately. Okay, g, we will write in terms of cosine sign, 1 minus c times 1 minus e power minus I km delta x. So this you all know, it will be cos km delta x minus I sine km delta x. All right. right? So this is a Euler equation something, I guess. If you have gone through complex analysis, so you can write e power minus I km delta x as cos and sine, cos km delta x minus I times sine km delta x. So we have a real part and we also have an imaginary part. So since we have both of this, that's why we go for this condition. So these conditions are both are same only, both are valid. So that's why what we will do is we will find modulus of g square, which is nothing but 1. So okay, let me write down separately. Let me write it down as a real and imaginary. Okay, 1 minus c, if you multiply in minus into minus plus c times cos km delta x, right? Okay, what would happen? Minus into minus plus c times I sine km delta x. All right.
That will be also plus, no, sir?
So there is
Last
a
step, plus C I sin KMD.
this is I minus into minus plus, and then there is another minus, right?
Yes, sir, you are right.
Okay. So is this right?
Yes, sir, you are
Okay.
absolutely right. Thank you, sir.
Right. Okay. Um. All right. So if I want to write modulus of g square, you can do it now. In the interest of time, I will just write it. So what we will do is we will just take the real part and square it, and we will add it with the imaginary part. Square plus c sine km delta x the whole square. So we always need g to be less than or equal to 1 for whatever the km be. So now we will try to simplify this equation more. So this to this conversion, there is some little bit algebra, you can do it on your own. If we simplify this term, how we will do it? This is, so 1 minus c, we will make it whole square, plus 2 into 1 minus c times c cos km delta x plus c square sine, sorry, cos square km delta x plus c square sine square km delta x, and these two term will reduce to c square, right? And we can simplify it as 1 minus c square plus 2 into 1 minus c cos km delta x plus c square. So we can expand this also, 1 minus 2c plus c square plus 2 into 1 minus c into c cos km delta x. If I make any mistake, please let me know. It will be 1 minus 2c plus 2c square into 2c times 1 minus c into cos km delta x. And how else you can simplify this? You can simplify it as 1 plus 2c into c minus 1, because 2c square minus 2c plus 2c into 1 minus c cos km delta x. Actually you can work out this on your own also. So this would be 1 plus 2c into c minus 1 into 1 plus cos km delta x, right? This is modulus of
Sir,
g
that
square.
could be 1 minus, no, sir?
Okay,
This
sorry, sorry,
could, the last step.
sorry, sorry, sorry. Yeah, yeah. write it as 2c 1 minus c. Is that fine? This should be minus, I guess.
No, sir, when you are
Should
taking 1 minus c, there it will be plus, minus 1 it will become.
is that fine?
Yes, sir.
Okay. So
Yes,
now,
sir. I feel it's okay now.
yeah, okay. Thank you. So now what we will do, we want g square should be less than or equal to 1. And how can cos km delta x vary? For any km delta x, what is the maximum and minimum limit of cos km delta x?
0 and 1.
So it can go from minus
Wait.
1 to 1.
Minus 1 or minus 1. Yes. Minus 1 to
Right.
1. Yes, right.
So
Yes. You're
yeah,
right.
so it can be maximum of this would be maximum would be 1. Okay. So if you substitute this 1 here, what happens? This term becomes 0, right? Let's say if you substitute minus 1 here, what happens? Come 2c into 1 minus c into minus 2, right? So this is the maximum. So this g square should be less than or equal to 1. So what are the possible ways that it can go above 1? It can go above 1 only these terms are above 1, right? So let me simplify even further. So if this is modulus of g square, okay, if it has to be less than 1, this term, let me remove these things, little bit confusing, I feel it. So if it has to be less than 1, this term has to be less than or equal to 0. Is this fine?
Yes, sir. Here.
Right. So then this term 2c into 1 minus c 1 minus c into minus 1 plus cos km delta x should be less than or equal to 0, right? That's what I just restated it, right? So I can take this minus on the other side, and I can write it as 1 minus cos km delta x, or you can keep it like that itself, not a problem. This should be less than or equal to 0, right? I just moved the minus here and there, right? Is this condition clear? We'll finish it in
For me, clear, sir.
yeah, we'll finish it in 5 minutes. Is that okay? Can I take 5 more minutes?
Yes, sir. Yes, sir.
Yes, sir, yes.
Okay. So
Yes, sir. Yes, sir.
yeah, thank you. So what we will do, this has to be less than 0. Okay. Now uh, uh, all the time it has to be less than 0. Now the variable is here km and delta x, but we know the function is going to be cos km delta x. And what is the maximum limit in between? Cos km delta x can vary from minus 1 to plus 1. Now let's say cos km delta x is equal to minus 1. Okay. Now what happens? The equation. Let's call this equation. Let's say let's not call it g. Call it 1. Okay. So what happens to 1? It becomes 2c into c minus 1 into 1 minus of minus 1, right? Which has to be less than or equal to 0, right? Is this clear?
Yes, sir.
So this has to be times 2, it should be less than or equal to 0. So 4c times c minus 1 should be less than or equal to 0. This is one condition we have. This condition, see, what is c? C is u delta t by delta x. Okay. And we have some delta t and delta x, and there is going to be u also something. So c can never be equal to 0, right? So if c is not equal to 0, what happens? C minus 1 should be less than or equal to 0. right? It's just 4c goes there. C minus 1 should be less than or equal to 0, right? C minus 1 is less than or equal to 0, C should be less than or equal to 1, right? So which means U delta T by delta X should be less than or equal to 1. Number 1. This is case 1. Okay. Now let's take case 2. Case 2 is cos Km delta X is equal to plus 1. What happens when it's plus 1? 2c times c minus 1 into 1 minus 1. It should be less than or equal to 0. This term automatically becomes 0 because 1 minus 1 is 0. So this term is always less than or equal to. It's a kind of trivial one. You no need to worry. And anything between plus 1 and minus 1 we are going to have. So if you were able to satisfy this ultimate uh, you know extreme condition, and if you are able to satisfy, which is already satisfied, if you are able to satisfy this condition, your scheme is going to be stable. That's what we will arrive at the result. So u delta t by delta x should be less than or equal to 1, or c should be less than or equal to 1. Both are same. This is what we call it as Courant Friedrichs Lewy number. Basically CFL number or Courant number. So whenever you run a simulation, you will actually find a CFL number, and you will make your delta t and delta x such that the CFL number everywhere in your domain at every time step will always be less than 1. So if you make sure that is happening, your solution is bound to be converged and your solution is bound to be stable. So that's what this condition tells. So you see, the analysis we did here actually helps us in understand that how should we vary delta t and delta x, how small should we have delta t or how small should we have delta x to get a stable solution. So this condition is called CFL number. So are you guys clear how I arrived with this?
Sir,
Right. Yes, Susan.
sir, can I
Yes,
ask
sir.
something?
Uh-huh.
Uh, Sir, means like this is for means like we have a study means like if we are running a simulation which is a transient one, right?
Mm-hmm. Yeah, it is for a transient one.
Yeah. So, sir, if we are not dealing with the time, means they are not dealing with transient problem. We are dealing with steady state problem. So, sir, how we can reach this condition?
So for a steady state problem,
Mm.
the stability issues is actually related to your discretization error. It's not actually round off error. If you see, these are actually round off errors, and uh, you know, uh, so if it is a steady state solution, you still have to have a mesh such that it can produce you a result. If you have a coarse mesh, it has its own numerical instabilities. So, but so hmm, if you steady state, yeah, good question. So how we will arrive at is, so in a steady state solution, what we will do is we don't have time step, but what we have is called iterations. Like from one iteration to second iteration, you will go. So based on the iteration also, error increases or decreases. So you can see t as a iteration, and you can again go through all these steps. Number one, or for a steady state simulation, um, yeah, there is no such thing called stability condition. Um, because there is no delta t, right? There is this CFL is for transient simulation, so there is no such thing called delta t. In a steady state, to have a numerically correct solution, we should have some. There will be some conditions. I'm not sure. I couldn't remember it, but I will get back to you. How to do is like what is the condition for steady state problems? Okay, is that fine?
Okay, sir.
I will give you a more comprehensive answer in the next section. Okay. I couldn't remember it. Anyway, so yeah, I will give that answer in next session. So is this like how did we arrive at this condition? Is this clear, everyone?
Yes, sir.
So if this is clear, so like this you can always do for each and every term for for a diffusion term. The lectures in lectures it's already been done for diffusion. We might have derived a condition like d should be less than or equal to half, something like that. We I'm not sure. Like it should be like there will be some condition for diffusion parameter. This d is actually diffusion parameter. And similarly, one second, Divagar, I will come back to you. Similarly, we will have we have stability condition for CFL number also. So basically, if you take care of these two conditions in any simulation, you will end up getting you know stable solution. Number one, and these are for always explicit schemes. If your scheme is fully implicit, you go through all these steps and you find the error equation, you find the amplification factor, and you end up getting uh, you won't end up getting condition. Your amplification factor would always be less than 1. So you will see that for yourself. Similarly, we did this for FTBS, like forward time, um, forward time and backward in space, right? We did this for FTBS. So FTBS, it's actually conditionally stable, and the condition is CFL number, right? So I recommend you all to be to do this same for FTCS, and you will see that it is unconditionally unstable. So there is no condition you can come up such that it will be stable. Okay, it is unconditionally unstable. Similarly, you can go with a few more schemes like so this is for explicit. You can go for implicit FTCS. You do the same thing for implicit FTCS. Only thing is it changes delta t here. So only thing is if we go back here, this is how you wrote the equation, no? So here we will have e power. So here we won't have 1. Here we will have e power a delta t. Here also we will have another e power a delta t. Okay. So if you take care of those things correctly, and if you end up with G, though the fully implicit will be unconditionally stable. Unconditionally stable. Similarly, you can try Crank-Nicholson. Few schemes like Lax-Wendorf, Lax-Friedrich. So those are few schemes which you can try. These would be in books also, like CFD books. You can try doing this stability analysis for each and every scheme, and you can come up with a condition such that it is stable. So if you have any doubts, you can stay back and ask. By this, I am concluding this session. Sorry for taking extra 10 minutes, actually 13 minutes.